Parijat from Bose, and she'll tell us about correlators in conformal field theory with defects.
I don't need that, right? Okay, thank you for the invitation, and it's a pleasure to be here. So today I'm going to talk about, am I audible? Okay, so this is going to be a slide talk, but I might use a Blackboard a few times. So I'm going to talk about a special class of conformal field theory, which is a conformal field theory with a defect inserted in it. And we will see how the defect breaks the symmetries of a conformal field theory and what is the consequences of that. And the main topic is going to be how to compute correlators in conformal field theory with defect. So this is based on this paper that appeared last month with Kaushik Ghosh, who is a postdoc at ENS. So I will try to go very slowly, and if something is not clear, please stop me and ask questions. So please feel free. So let's start with the idea of defects and why do we care about this and what is it good for. So defects are usually present in physical systems, and defects describe impurities in physical systems. So to orient ourselves, we can think about some specific examples. So for example, we can think about the Kondo effect that was studied by Kondo in 1964. And this is due to the presence of magnetic impurities in metals. So if we have a metal and we put some magnetic impurities, then the whole thing behaves differently. So it affects the properties of a system, and that was studied by Kondo. Now, this Kondo effect historically has been very important in the context of quantum many-body physics. So the Kondo problem actually motivated Wilson to develop or think about the renormalisation group approach. Now, there are other kind of defects that we can have. So for example, we can think of a lattice. So the lattice system, we can think of this as the critical point. So we tune the temperature such that we have an ordered phase and a disordered phase in the lattice, and we are precisely focusing at the critical point. And this lattice system can have boundaries which is bounded by, say, some planes, or it can have interfaces where parts of the system are separated by some domain walls. And the idea of these boundaries and interfaces is to capture the finite size effects of this system. So this was also studied earlier in the 70s, so by Bray and Moore in the context of semi-infinite systems. So these defects can be of different types depending on the shape and size of the defects. So we can have line defects, surface defects, and so on. So let's talk about the lattice system with the boundaries. So on the left we have this figure. So we have a three-dimensional lattice, and we can imagine that this lattice is bounded by two planes. So this plane and this plane, so these are marked as dark. So these are the boundaries of the lattice, and these are orthogonal boundaries. And we can imagine that we have spins at each lattice site. So each of these lattice sites has a degree of freedom spin, and it interacts with the other spins. Now, the way the spins interact amongst themselves depends on the position of the lattice site. So the spins, if the two spins are in the bulk, say for example here and here, then the interaction is different from the interaction when one of the spin is in the boundary. So this interaction between this spin and this spin is different, and also the interaction between cross boundary spins like this one and this one. So this is the lattice system with boundaries, and here in the right we have also another lattice system, and again this is a two-dimensional square lattice, and at each lattice site we can have some degrees of freedom with some specific properties. And here we have some impurity, so this is marked as this red dot over here. So this means that this degrees of freedom is different from the degrees of freedom in the located in the other side. And this impurity can interact in with these other spins in many ways. So
if you repeat from the left, because we want to think of the boundary as some defect.
yes, sorry. So this is a three-dimensional lattice, and we put some boundaries. So this these are not infinitely extended systems. So we have put some finite boundaries in this or in this. So this here we have actually two orthogonal boundaries, but it can have only one boundary in one direction. And because of these boundaries, this we can think of this as a defect because it breaks some of the symmetries of the entire system. I will talk about the symmetries that are broken by the presence of these boundaries. But these are the defects, and they capture the finite size effects of the system.
The degrees of freedom in the bulk and boundary will be different.
It can be, so here it can be different or it can be the same, but the thing is that the way it interacts, it can be different. So the spin here can interact, so it will have an interaction energy like if these two spins are in the bulk. So here this is the bulk without boundaries, but on the boundary, the spins can have a different interaction energy. Does that answer your question? Okay, so the thing that we are going to discuss today is how do we describe the dynamics of defects or impurities in a system. So this is a brief outline of my talk. So I am going to begin with a broad overview and motivation of the defect system that we already know, that is already there in the literature, and how do we describe the dynamics using the approach of quantum field theory. And then we will talk about a particular class of conformal field theory, which is described by this cubic anisotropic model. I will discuss in details the symmetries of this model. So, but this is described by a conformal field theory. And after introducing this model, we will discuss the effect of line defect in this system. So we will break the conformal symmetry by this line defect. Then with this setup, we will go on to compute the correlation functions in these defect CFTs. So the observables that we compute in this kind of quantum field theory is the correlation functions. And we will compute these correlation functions using two complementary approaches. So in the first part of my talk, I will discuss this from using the Lagrangian formalism. So we will start by writing down a Lagrangian relevant for the cubic anisotropic model with the specific symmetries. And then we will discuss how the defect can play a role in the renormalization group flow in this model. And then towards the later part of my talk, I will discuss this cubic anisotropic defect system from the point of view of symmetries and consistency conditions. So this is going to be a Lagrangian independent approach. So we do not care about the specific details of the system, but we will focus only on the symmetries, and we will see how to use these symmetries efficiently to compute the correlation functions. And we will also talk about the connection between these two approaches. And finally, we will summarize with some open questions and future directions. So let's start with the overview. So we are interested in a bulk conformal field theory at the critical point. So we we know that a system at a critical point is governed by a conformal field theory, and we will be talking about a conformal field theory in the space-time dimensions. Now, the symmetries of a conformal field theory includes translation, rotation, scaling symmetry. So the system looks the same irrespective of the length scale. So zooming in and zooming out does not make any difference. And there is special conformal transformation, which is translation conjugated by inversion. So all these symmetries add up to give us the conformal group, which is invariant under SOD plus 1, 1. So now what we do is we introduce a defect in this d-dimensional system. So for our purpose, we think about planar defects. So imagine that we have a p-dimensional plane and we put this plane in this d-dimensional space. So this is the p-dimensional plane, and we can have, okay, I can use the board to, so we can have coordinates on the plane or the and the normal to the plane. So this is p dimension and these are the normal directions. So if I can also use that part also if, okay. Okay, so with this and the normal directions will have d minus p coordinates, so we can separate out the coordinates like this. So this will have a coordinates on the plane and I coordinates on the in the normal direction. So a runs from 1 to p and I runs from p plus 1 to d. Now, what are the symmetries that are preserved in this system? So we have placed this defect. So some translational symmetry normal to this direction is broken. So PIs are broken normal to this direction. So these are the translational generators. And similarly, this direction will also have a special conformal generator because that is also that involves also a translation. So the special conformal transformation along this direction is also broken. And what about the rotation? So these are the rotations in the bulk conformal field theory, and when we use these defects, so everything can rotate on the plane, so that is still preserved. So Mij is preserved, which is in this plane. MAB is preserved, but the cross components are broken. And similarly, the these generators PA, KA and D, these are also preserved. So the scaling remains unchanged, but also the momentum and the special conformal transformation along this defect is also preserved. Okay, so with this, you can switch off the light if you wish. So with this, we end up getting the symmetry.
So in that point, keep this on. If you're going to use the board again, because that light can get turned on. If the other you can switch it on.
It's not working. Okay. So with this, we can see that the defect preserves a p-dimensional conform Poincare symmetry on the plane, rotations in the transverse or normal d minus p directions, and the scaling symmetry. So we end up getting this residual symmetry. So we started with this bulk SOD plus 1, 1 conformal group in d dimensions, and the introduction of this p-dimensional defect breaks it to a SOP plus 1, 1, which is basically the conformal group on the defect, and this is the transverse rotation. So to define formally, defect conformal field theories are conformal field theories where part of the symmetries are broken. And for our purpose, we will only be interested in line defects, so P is equal to 1 for our purpose. So let us first try to understand the defect CFTs from symmetry point of view. So here is a picture. So we have this d-dimensional bulk conformal field theory, and when I use this word bulk, it means that this is the conformal field theory in the entire space-time dimension. So it has nothing to do with holography. So whatever I am going to talk about applies to any generic conformal field theory. And in this bulk CFT, we introduce this line, which is the line defect. So we can divide the coordinates like this, as we have done here. So we have one line, so let us call the coordinate on the line, this is the tau coordinate, which goes along this direction, and the rest are, we call it x mu. And this line defect is located at x equals to 0. Now, one important point to mention is that this defect breaks translational invariance in the normal direction. So we will not have a conserved stress tensor in the bulk. So what are the operators that we can have in this setup? So in conformal field theory, we usually talk about things in the language of local operators. So with this defect, we can have two classes of operators. So we have bulk operators, O, which lives in the entire space-time. So it depends on both tau and x. So these are two bulk operators. We can also have operators on the defect. So these are localized operators, and I have used this hat to denote that these are defect operators. So these are the defect operators that can only live in on this line. So they are function of tau only. So these operators, we can think of this as living in a one-dimensional conformal field theory. So I will talk about this in details in the later part when we discuss the bootstrap framework. So we see that this defect structure has richer structure than usual conformal field theories, because we now end up getting different observables in terms of the bulk and the defect scaling dimensions or other correlation functions. So, and these operators can have complicated interplay between them, and one can study the constraints of on the correlation functions of these defect and bulk operators using just the symmetries and consistency conditions. So this is the symmetry structure that we can use to analyze the correlation functions of these defects, and this is the idea of defect conformal bootstrap. So it was initiated in the context of boundary conformal bootstrap by these authors in 2013, and then subsequently studied in the context of defects in 2014 by these authors. So that's about the defects from the symmetry point of view.
So Parijat, you really considered local.
Yes, yes, yeah. Okay, so now the defect conformal field theory can also be studied from a Lagrangian point of view, where we start with a specific Lagrangian. So this is how we have defined the defect conformal field theory. So it has a bulk part and a defect part. So the Lagrangian can also be decomposed into separate parts. So this is the bulk part of the Lagrangian, which contains the bulk degrees of freedom that lives in the entire space-time. And here we have the defect part, which is localized on the defect. So as you can see that here is a delta function with this argument, which is the position of the defect. So this part survives only when we are on the defect. Now, this can be, one can think of this as some kind of deformations, and we can study actually the renormalization group flow under this deformation, and similar kind of deformations were studied when this theory was deformed by line operators, and it was shown that they can undergo a non-trivial RG flow with some non-trivial fixed points. So it was studied in 2014 by Elias and Sajdev, where they have some coupled fermions coupled to some scalars. And recently it has also been studied by these authors for some globally symmetric conformal field theory. So here is the renormalization group flow approach. So on the left we have a picture for an RG flow in conformal field theory. So this is a conformal field theory without a defect. So we know that conformal field theories are endpoints of RG flows. So a quantum field theory can be thought of as an RG flow from a CFT in the UV to another CFT in the IR. And here on the right we have an RG flow in terms of a defect. So as I have already mentioned that the defect can be thought of as a relevant perturbation, and this relevant perturbation can trigger an RG flow. So in this case we can have an RG flow from a defect CFT in the UV to another defect in the IR. So the question is whether one can have some non-trivial fixed point in this setup. And
are all defects like available with pressure, or?
Are all defects what? Relevant, yes, yeah. So and when we talk about this defect flow, we assume that the bulk is at the particular fixed point. So we do not change the critical point of the bulk CFT. Now, our goal is to study the correlation functions in a conformal field theory with a specific kind of global symmetry that I will talk about now, and to see if there is a defect, non-trivial defect fixed point. Now, before going further, I just want to mention this point about the defect RG flow, which is the irreversibility of the defect RG flow. So one can actually compute a quantity which decreases along the defect RG flow. So it was first conjectured by Affleck and Ludwig in 1991, and in the context of a conformal field theory, and then it was proved by Frieden and Konieczny in 2004, and later on this proof was also discussed from the point of view of quantum information theory. So what is the RG flow? So we can actually,
Oops, are valid in general damage?
yes, so this in this paper they have proved that this is a general dimensional statement. Yeah. So the earlier proofs were in 2 dimensions.
Only line defects or?
They have shown this, yeah, only for line defects, yes.
So what do you mean by reversibility?
Yeah, so when we flow from a UV fixed point to an IR fixed point, there is a quantity that decreases monotonically. So it's just like the entropy, if it's unidirectional. Yes, yeah. So this quantity always decreases along the flow. So here is a partition function of a CFT without any defect, and here we have the partition function with this line defect. So we have this the relevant deformation along the line. So phi is a relevant operator and H is the defect coupling. So this is how we perturb the CFT and end up getting a defect CFT partition function. So with these 2 partition functions, one can compute this quantity, the ratio of the defect CFT by the CFT thing, and this quantity captures the impurities due to the defect. And this is defined to be log of G, which is called the G function, and one can show that this quantity G is monotonic. So GUV is greater than GIR.
Defects here, right? Why are you calling one ZCFT and one Z defects?
This one is without the defect. So here we have,
Defect or without the pattern?
yeah, this is without the defect, there is no defect. And here we have we have deformed the theory by this relevant perturbation.
But this relevant perturbation exists only on the defect.
Yes, it's along the on the defect.
So without the defect, I mean,
So this is just a pure conformal field theory with the conformal symmetry.
So I think the question is if the DCFT is not quite partition function of the effects here. It also has the bulk part.
Yes, it has the bulk part.
So there, yes.
no, but my confusion is normally what I have seen is that you start with the defect CFT,
Yes.
then you put on a relevant perturbation on the boundary, on the defect,
Yes.
right? And then you flow, right? And you calculate the ratio of the two things. One is called GUV, one is called GIR.
Okay, so maybe the terminology is, so what I am doing is I am starting with a CFT without any defect. So there is no defect degrees of freedom in this. So this is entirely the bulk degrees of freedom. And
I guess when you're not showing the deformation. This is just I think, so ZDCFT by ZCFT is the thing of the defect CFT, and then you further add a perturbation and then run.
okay, yeah.
So here there is no running. There is just
Yeah, but then if you do that, then the ZCFT part will cancel out. Right? So ultimately, what you compute is ZDCFT over ZDCFT not or something. Because
DCFT not, yes. Yeah,
right?
yeah.
Where you have the defect but no part.
I am a bit confused. So we can have a defect.
You said the H equal to 0.
Yes, so that is like a trivial defect, we can
But
think.
H equal to 0 is not trivial defect, right? It's trivial perturbation on the defect, isn't it? I mean, that's what I'm.
H is the defect because here
So H is the defect.
H is the defect coupling, and this phi is the.
so if you define G this way, and then there's a GUV, and then there's a GIR.
I think, yeah, what is flowing against what? Because you have not added any coupling or deformation.
So this is the deformation.
Yeah.
This
so
is.
This is a deformation.
Yes.
To define this deformation,
Yes.
you need a defect because phi
Yes.
is the defect operator, right?
Phi is the operator that lives on the line. Yes, that is the defect. Yes,
So
yes.
if there is no line to begin with,
Yes, then that is a, yeah, that I would call a trivial defect, if there is no line.
but suppose there is no line, there is a line,
Yes.
but H is 0.
Okay.
That is what.
Okay. Okay. Yeah, I understand. So if there is a line, but there is no relevant perturbation, then that is again a defect CFT. It breaks all the symmetries, but that is not what we are considering. That
Because that I thought would be GU, what you would call GU.
yes,
Right.
because that is like adding no defect or trivial defect, I would say.
Defect but no perturbation.
Right. Right. Yeah. Yeah. I would call this a trivial defect.
ZCFT has the defect but no perturbation. Is that correct? Because if you put H equal to 0 and ZDCFT, that gives it.
Sorry, if I put
That if you say H equal to 0 here,
yes.
that gives you back the first line, right?
Yes, it doesn't have the perturbation. Yes.
Yeah, but it has a defect.
Okay. Okay. I understand the confusion. Yes. Yes. That's right. Yes. Okay. Yeah.
So what does it mean to say it as a defect that there's a boundary condition on the bulk fields?
The defect will have some boundary conditions. So what I am doing is so for our purpose, we are just localizing the bulk field on the defect. So that is the kind of perturbation that we are adding. But one can actually,
First line, ZCFT. Is there a boundary condition on the defect? In the path integral, is that
so here is actually no defect in my language. This is,
okay, but this is different from just doing a bulk scheme.
so you are,
You said H equal to 0 in the second line,
yes,
right?
yes,
then that doesn't give you just the bulk CFT. It gives the bulk CFT plus a defect
Without any relevant perturbation, yes.
right?
But these are, I think, two separate things.
For h equal to 0, are you going to get back ZCFT?
Yes,
You will, right?
yes,
So then what you are calling ZCFT is a defect without perturbation.
yes,
That you have the defect but no perturbation.
yes.
But that
But if-
information has gone in only the measure, right? In the
Yes, yes, yeah.
DeFi boundary condition.
Yes.
At the defect and at infinity or
No, not doing the measure only. I mean, the point is, defects are like, I mean, if you think of 2D CFT, defects are like deviance. You put a boundary, right?
Right, and it will change the structure of the correlation function.
Which is the structure of the code.
Yes, yes,
Now on that D brain, you can switch on some perturbation,
right,
right?
right,
Which will may reduce the tension of the D brain.
right, right.
So this GUV and GIR are the
With the perturbation and without
with
the,
the perturbation and without the
right, yes, yes,
So from that perspective, I would say that the ZCFT also has a defect. But
yes,
you just haven't switched on any part.
right, right, yes, yes.
But the information on the defect is only the measure, right? Because S0 is just the usual action.
S0 is the action with, I mean, the worksheet action with the boundary condition and everything else which I put in. But no
Yeah,
perturbation.
boundary conditions.
Yeah, no perturbation.
Yeah, so it's the same action that you would have not written without the defects.
No, no.
Uh,
It's not the same because once you put the defect, the boundary, you are defining that you are in a defined space already, right? It doesn't make sense to say the same action.
And it's the same Lagrange.
the structure will be different, the correlation function and all those things will be different if we have a line in this setup.
Same Lagrangian, but not the same.
Not the same action, yeah. So it's like you are doing on a half line. If you take this
Right,
here,
right,
work on a half line rather than a
yes, yes.
So, do you have extra degrees of freedom dealing on the line effect?
No, I mean for,
You have bulk fields, you have
yes, yes. So for this talk, yes. But in general, one can have extra degrees of freedom localized on the defect that can be different from the bulk degrees of freedom.
So then if you put h equals to 0, it just becomes HCF.
So it's like if you have a D brain, it's not ZCF. You have a theory with D brain and without D brain are different background, right?
So when you impose some kind of defect, even if you are not adding the perturbation, you are altering the structure of the space-time, right? So
when you put D brain, you put some boundary conditions, right?
Yes, you put some boundary condition.
So
But no perturbation. You are not adding any phi.
okay,
Now if you switch on some electric some field on the D brain,
that's like a part.
that's like a perturbation. Then you are switching on a phi. So you can put a cos x perturbation on the D brain. That will be the analog of the phi.
So any more question?
Maybe you don't want to talk about it, but can you roughly tell us how this you show the monotonicity? Is there some secret to understand?
How to prove this? They actually proved this in this paper. So they have some kind of gradient formula that they have shown that for a positive definite unitary CFT, it has to be.
Is it like very similar to the Zamolodchikov?
Yes, yes, yeah. It's
So you construct a quantity and you show that
right.
it's,
This decreases along.
derivative is some
Right,
sign definite quantity.
right, yeah.
And that so at least in Zamolodchikov theorem you are seeing the tangent.
Yes, here also it is it is assumed that it has to be, yes, yeah.
Sorry, this one. So
Yeah.
in there, like you basically relate it to some TT.
Here also they exactly do the same
So there is some
kind analog of the,
energy momentum tensor on the word line.
right,
Which are
right,
related to one.
right, yeah.
And this statement which you have written is true for, I mean, it's not just true for line effect, it's true for in general, I mean, GUV.
What they have shown is that this is, they have proved that this is true for this line defect, but
The line is compact or non-compact.
no, they have said that any conformally equivalent manifold will have the same property, yeah. But for other kind of defects, like if you have surface defects or higher dimensional defects, I think that is still not that robust. Yeah. Okay, so now let's talk about the specific model that we are interested in, which is a cubic anisotropic model. So why do we care about this model? So this model is relevant to study the critical behavior of anisotropic cubic system. So this is a paper by Amnon Naharoni from 1973, and as the abstract says, what this does is it studies the critical behavior of ferromagnets and ferroelectrics with the Hamiltonian with this cubic symmetry. I will discuss the cubic symmetry in a bit. And what they have done is they have studied this model using the renormalisation group approach in 4 minus epsilon dimensions with specific n component spins with this symmetry. So what this model does is that this describes a phase transition from a cubic to tetragonal structure. So this is relevant to study the second order phase transition in perovskite materials. So what are the perovskites? So these are materials composed of two ions A and B. A and B can be different ions, and 3 oxygen. So this is the unit cell structure of the perovskite, and this is the structure for strontium and titanium. So A is strontium and B is titanium, and this is the unit cell structure where the strontium sits at the corners of this cubic lattice. So this is a cubic lattice, and here at the center of the cube we have this titanium ion, and inside the cube we have this octahedral structure which consists of these oxygen atoms. So this is the octahedra, and everything surrounds this titanium ion inside. Now this model, so this is a particular kind of crystallite structure in this perovskite material. Now if we lower the temperature of this material, it turns out that this undergoes a phase transition, and this cubic structure is altered to a tetragonal structure. So this is a tetragon where the length of, so this is the base. So base is still a square, but the length is different from the height. So this is that's why we are having this transition from cubic to tetragonal. And in during this phase transition, this octahedra rotates around the axis of the cubes. So this kind of symmetry, this is relevant to study the structural phase transition. Yeah, I will talk about the field, the order parameters in the next slide. Yeah. But the bottom line is that when we undergo this kind of phase transition, the full rotational invariance is broken, because this octahedra can rotate along the axis of the cubic lattice. So we need to incorporate this symmetry. So how do we do that? So this is the field theory model that can describe this phase transition. So we have a scalar field theory. So this is the order parameter with n components. So this is phi I runs from 1 to n, and we have a generic quartic bulk interaction. So in this model, the ON symmetry, which is the symmetry that we have when we have rotational invariance in the ON fields, that symmetry is broken. So here is a Lagrangian. So this is a Lagrangian in d+1 space-time dimensions. So this is the kinetic term, and here we have this term phi I square whole square. So this is like a phi to the 4 interaction term with the interaction coupling being G1. So these two terms, they describe the ON symmetric Lagrangian. Now we want to break this ON symmetry in such a way that the structural phase transition can be incorporated. So this can be done by adding this kind of interaction, which is phi I to the 4 with this new coupling G2. So these two terms together tell us that this is no longer rotationally invariant along the rotation in the phi space.
What is the symmetry that you brought
Octahedra, sorry, from cubic to tetragonal, yes. So
That's a spontaneous symmetry.
no, that is
This is a spontaneous symmetry.
no, this is explicitly broken.
Explicitly broken by some extra
Yes.
forcing.
Right.
Is this a first order?
No, it's a second order. Yeah. So it was first observed probably in the 60s, and there is a universal.
So then the Lagrangian that you're trying to write down describes both the phases, just to make sure I'm not.
Both the phases, meaning the first order. No, this is very specific to the second order transition. So I have, we are precisely at the critical point. There is no mass term over here. So we have tuned the mass term to 0.
The question is, what is the symmetry of this Lagrangian?
Yes.
It is a discrete symmetry. There is some discrete symmetry.
So it's rotation along the 3 axes of the cubes. So the cube has some particular crystal structure, and that breaks the rotational invariance. So that takes care of this term. So it's
So it has the same symmetries as the cubic.
yes, exactly. Yeah, this is the model for the. This is the model to study the cubic. Yes.
But it has more symmetry than the tetragon.
More symmetry in what sense?
The peekaboo.
I'm not sure.
Okay, you say that what values phi should take to describe both the phases.
Yes.
So what values does phi take? So phi is 0, the critical point, I understand. And then how do you go to this phase to that phase?
By tuning the couplings. You mean from the
Vacuum
cubic?
expectation value changes?
Expect.
The vacuum expectation value of phi changes, or that's not the way?
I am not sure. Okay, I understand the confusion. Maybe I have a diagram for the different fixed points that can be there. So probably that will. But I didn't understand this. That it has a.
Confusion is that this Lagrangian has some symmetries.
Yes.
Right?
Yes.
And the question is, how does that symmetry relate to the symmetries of the diagram that we showed in the last?
Okay, so yeah. So here in this diagram we have this cubic lattice structure. Now when we go from this phase to this phase, this octahedra rotates.
Yeah, but let's just look at the left hand side diagram. So this is a cubic symmetry, right?
This is a cubic symmetry, yes.
There is a discrete symmetry of this.
Yes,
lattice, right?
yes.
Is it the same symmetry that the Lagrangian that we wrote down has?
No, but here if we do not rotate this, that rotational invariance is not broken. No?
No, rotational invariance is always broken to discrete rotational invariance, right? Because this doesn't have continuous rotational invariance.
I mean, what I mean by rotational invariance is in the phi field space, ON space. Yes. Yeah. So sorry. So yeah. When I talk about rotation, I mean that this is the ON field. So this is the rotational invariance of the order parameter that is broken.
What is the phi here? Let's say if I given this, how they measure phi? It's like should be some should be some difference of 2 sides lengths or something like that, right?
Yes, so this is like what we do in Ising model, kind of this. So the difference.
Yeah, in Ising model we just have a magnetization.
Yes.
And that is the continuum theory.
Yes. So here also we have a continuum theory that is described by that Lagrangian, and that.
What is the discrete?
Similar, what degree of freedom is the ON vector carrying this phi I?
N, what is N in this?
Okay, so we can, so in 3-dimensional space we can think about that n is 3, because this octahedra can rotate around any of these cubic axes, x, y or z. So we have 3 order parameters. So this is like O3 model, but with a crystalline structure which breaks the O3 symmetry in the space of the order parameter.
Think of the order parameter as some orientation of this.
Yes.
This operator thing.
Yeah, so this order parameters are like, we can think of this as the Ising model thing only, but with some specific assumption that this symmetry is broken. It's not the symmetry of the Ising model.
If the last term that Lagrangian is turned on, you're saying you're going from this phase to that phase.
Last term is turned on, yes. So that describes the phase precisely at the critical point.
See, the last term actually breaks it to a discrete symmetry. So if you are saying that in 3 dimensions this is O3.
O3, yes.
Right? So if you go back to the Lagrangian,
Yes.
you said n equal to 3,
Yes.
right?
Yes.
Then the symmetry,
Yes.
isn't it the same as that of the cubic lattice that you showed? The symmetry of this Lagrangian, what is the group? Symmetry.
So for O3,
No, this doesn't have
O3 plus this part.
Yeah, because of that part, O3 is broken,
Yes.
right?
Yes.
To a discrete symmetry.
I mean, okay, so your question is whether this cubic symmetry is a discrete symmetry or?
Cubic symmetry is discrete
Yes,
symmetry.
yes.
Or that's the same symmetry as that Lagrangian.
Yes, yes,
So this Lagrangian has the same symmetry
yes,
as that.
yes, yeah.
And for the other side, the right hand side diagram, is it the same symmetry group there?
Yes,
So both of them have exactly the same symmetry.
yes.
Both are.
Yeah,
But tetragonal lattices are less symmetry.
but this structure is broken already, no, by this.
But it has even less symmetry than what you've broken. See, you've broken the rotation to cubic,
Yes,
and further cubic has to be further broken to tetragonal.
yes, that's the transition from there to here to there.
Yeah, but that is not shown in this Lagrangian. Sorry, that will be some spontaneous.
Okay, okay, now, oh yeah, I understand that, yeah, yeah,
So this has an explicit cubic symmetry,
yes.
and then it probably breaks for depending on the G1, G2 values.
Yes, yes,
Spontaneously,
yeah,
the cubic
it will be
symmetry
like
further
the
broken
Ising,
to tetragonal.
right, yes, yeah, I'm sorry for the confusion, yeah.
But you're saying this is a vector order parameter.
This is a vector order parameter, yeah. It is the fixed point, yeah, it will probably, I will try to discuss the fixed point structure, then maybe we can see the interplay between the known stuff. So this model can be studied using using this approach of Wilson, where we can study a theory instead of 4 dimensions, we can study this in 4 minus epsilon dimensions, treating epsilon to be a perturbative parameter. So here is the fixed point structure. So here we have 2 couplings, G1 and G2. So this is a picture taken from this book by Aharoni, where we have this G1 fixed point, G1 along the x-axis and G2 along the y-axis. And these are the 4 fixed points. So we have the trivial Gaussian fixed point when both G1 and G2 are turned off. So this is here at the origin. We have the Ising fixed point when G1 is 0, but G2 is non-zero. So what happens when G1 is 0, this n interaction term is gone, but G2 is non-zero, so then we can have n scalar fields with each with the Ising kind of structure. So this is the Ising fixed point over here.
Actually, n copies of
N copies of, yeah, n decoupled Ising model, yes. And this is the ON fixed point where this term is not 0, but this term is 0, but this is non-zero. So this is the ON fixed point, it's also called the Heisenberg fixed point. And finally we have the cubic fixed point where both these couplings are non-zero. So this is the cubic fixed point. And one can calculate the values of the fixed points in this Wilsonian, using this Wilsonian dimensional regularization approach, and it turns out that the fixed point values, they are like they start at order epsilon. So what I'm saying, why I'm mentioning this, it will probably become clear in a couple of slides. So throughout the talk, we will only be interested in this cubic fixed point where we turn on both G1 and G2.
Here you're saying there are two relevant. One of them is relevant, another is irrelevant. Like to understand these arrows. Okay, we talk.
Yeah, here. So this is a stable fixed point. Yes.
It has
Yes.
no relevant.
Yes. Yeah.
Only irrelevant.
Yes. Okay, so yeah, as I have already mentioned that this reduces to the Ising model. For n equals 1, we have only one scalar fields. And when n equals 2, this there is a special symmetry that we see in the space of phi 1 and phi 2. So this transformation, the transformation of these fields in by an angle pi over 4 makes this leaves this interaction term invariant if the couplings are transformed like this. So with this transformation, the Ising fixed point is transformed to a cubic fixed point.
So you're saying n equal to 2 is also decoupled, right?
Yes,
But
it's transformed from the Ising to cubic. So this is like kind of getting back the Ising fixed point.
yes, this is. But there is an RG flow from the Ising fixed point to the cubic fixed point.
Let's see. So here to here.
Yeah. So
But so here we are not turning on any other relevant deformation that can take us from here to there.
and I'm just trying to understand because if they're equivalent, then how this is constrained?
Okay, so there is this constraint. There is a value of n that one needs to tune. So all of the position and the location of the fixed point depends on the value of n. So whether the deformation is relevant or not, that is also controlled by the value of n. So what is? So one can actually try to compute all these fixed points and see. So these fixed points are computed using the value, using a generic value. And then one can see that when it changes sign. So if I remember correctly, there is a term which is like n minus 4 in this fixed point thing. So for n less than 4, it behaves differently than for n.
The beta functions at arbitrary n
Yes,
with the epsilon expansion.
right.
And then you said it is.
Yes. And that's where the independence comes in.
You said something about the epsilon order term. So this is all of the epsilon order term in the beta function.
Yes.
So it doesn't exist at 4D.
Exactly in 4D, no. So in 4D, this is the free theory. This is a generalized free theory. Okay, so any other question about this? So, okay, so now we can try to talk about the renormalization group flow that we.
Through the line defect. You're talking about the line defect in this here?
Yes. So we have this cubic, we have this symmetry structure, and now we'll add a line defect.
So you're at the cubic fixed point.
Yes. So now we will sit at the cubic fixed point, that is the bulk fixed point that is fixed forever. And now we see how does the line defect take us from one fixed point to another.
That's like the critical values of G1 and G2.
They are same. They are all.
Go to 1 must.
It's
You want to look at the three-dimensional lattice.
they're not one, but there are some.
No, epsilon.
Yes, yes, yes. So
The analysis in
yes,
epsilon, but you
yes, yeah.
do 3 dimensions.
Yes, yes, that's true. Yeah. So those values, so the G1 and G2 fixed point, those values are already there. In using this bulk Lagrangian RG flow, one can actually compute the beta functions of G1 and G2. So now what I'm saying that with these beta functions, we already know that this is a bulk cubic fixed point. Now we are going to add a relevant deformation so that the theory can or may or may not have a defect fixed point. So that is something that we are going to check.
So it doesn't have any local relevant information. We're going to do a defect. Like that.
This is in.
Showed that all arrows came to the fixed point. There is no relevant information. By that I mean, I guess there is no local object.
That was, yeah, that was without the defect.
But still there could be.
There could be yes, yeah, that's true. Yes. Yeah, sorry about the confusion. Yeah. So.
You said defect to be like defect with random information, right?
With the relevant information, yes. So here we, so this is the bulk Lagrangian that we had, and now we are adding this relevant deformation. So this is a defect operator which is localized on only along the line.
But first, don't you have to say what the defect is before you introduce the operator?
This is a line defect, so at x equals to, so we put a defect at x equals to 0.
By putting some boundary condition on the phi 1 and phi
Phi 1,
But those fields, phi I. You have to put some boundary condition on the phi i's to make the defect, right?
yes.
So you have to specify what those boundary conditions are or not?
I don't think at any point we have used that.
But that phi I is the same phi, no? But
This phi I is the same phi. So here we have bulk n scalar fields, and out of these n scalar fields, we'll single out one particular field. So we break the internal symmetry, and using that field, we deform this action. But we don't.
Suppose it was a 2D sphere, just a p scalar.
Yes. Yes.
Just 2D sphere.
Yes.
And now you want to create a defect.
Yes.
You can put either a Dirichlet boundary condition
Yes.
or not boundary.
Yes. Yes.
So that has to be specified, right?
That has to be
What kind of
specified.
defect you have.
Yes.
Then you can start perturbating.
Yes.
Put a
But I don't think we have. No, this. No, I don't think this is required here.
Have a charge particle which is going on the line. It's couple the bulk cage with the line. There we don't really.
Do you know what this corresponds to in the original perovskite? Are you just removing some structures?
With this, no, we do not know. There is no. Okay, one thing can happen that we have some other atom which is placed inside. So if you remember the first picture that I showed, so in this maybe in the first slide I have shown this picture of some impurity. Yeah. So here we have some. So this is a two-dimensional lattice. We have some degrees of freedom at each lattice point, and here we have some defect, which is a different degrees of freedom that than the others. So
this would be like say you just replace titanium by
some yes.
You replace titanium by some.
Ideally, yeah, that would be the case, but we are not. I don't know if there is any experimental study on this defect cubic symmetry. Theoretically, there are some studies, but not experimentally. Yeah.
Not in place, but just add.
Yeah.
It's just at one point at the origin, and then it's line.
Yeah.
In space time, it's a line.
Yes.
It's more like an impurity rather than a junction.
Right.
Can you read a
Right. Yeah.
But if you are doing it with DCFT, then it's like a boundary, right? Meaning it's there you do need a boundary condition. Could it be that
Boundary.
basically you are using normal boundary condition on phi 1?
I don't think we have actually used that anywhere. Because this is some kind of field that is localized on the defect. So
Maybe the boundary condition just comes from extremizing this action. Whatever extremizes this action.
But even when we have a boundary, so in usual CFT with a boundary, if we have an action, then we specify the boundary conditions on the fields, but this is not the case.
No, but once you have an action, the variation principle sets also the boundary condition. Include the boundary terms on correct.
Yes, but that is something that we impose, right? It's
But in 2D, for example, you can use either DDC or normal, both are allowed.
Right. Yeah, the same action on the
Does it have to do with the fact that this is some high co-dimension thing?
Yeah.
Side effect is like a boundary in 3 dimensions, for example. It doesn't separate into regions.
so I'm trying to think where will that boundary condition play a role, because it is not clear, at least from here, that it will play any role.
But this also includes either.
Sorry?
This does not include 2D, is in the action, 3 minus.
Yeah, it's usually it's greater than 2. Okay, so yeah. So now I'm going to the main part of my talk, which is computing the correlation functions in this theory, where we treat the bulk couplings perturbatively. So G1 and G2 behave perturbatively. So, and this defect coupling is exact. So let us try to see how the defect renormalization group flow can take place. So the first thing that we have to do is we have to renormalize the defect coupling. So we have to renormalize, so we have this new term in the action and we want to renormalize this. And as I have already mentioned that the bulk theory is at the cubic fixed point. So the renormalization constants for the bulk theory remain unchanged by the addition of the defect. So now we need to compute the boundary renormalization associated with the line defect. And the demand is that the 1-point function of phi 1, the defect operator, this is finite as epsilon goes to 0.
Just one comment.
Yes.
The statement that the renormalization constants in the bulk theory remain unmodified also has to do with this codimension of the defect. If it's like a codimension 1, like a boundary.
Yes, yes.
Then I think it may change the
Because even there, it doesn't really change the
phase.
yeah, the boundary, the bulk, because it's like if you make a deep brain on in a CFT, you can switch on multiple various kind of information on the deep brain. But the bulk CFT remains unchanged, right? This takes you from D1 to D0 or might something between. That statement I think is true even for codimension 1.
But for the, this is, I'm still not getting where is the boundary condition, because we did not use it anywhere at any point.
Yeah, so the question, how do you compute this?
Yes. Okay, so yeah, so these are the diagrams for the 1-point function.
So this propagator is what boundary conditions you use?
The propagator is the bulk propagator with 1 point taken to the boundary. To the defect, sorry, yes.
So it's a boundary to bulk propagator.
Yes.
But I think what he is saying is that it's the same as bulk to bulk.
Yes, exactly. We just take 1 point to the limit of.
You just take the usual bulk and you just take the bulk point.
Right, exactly.
Like,
There is more like to Wilson line as saying.
Yeah.
That you are just computing some line of operator but in the bulk. In the bulk here, that you have like
Yes.
line integral.
Line
is
integral.
operator
That's true.
in the
Yes.
bulk here.
Yes. Yes.
So then you can think of this as a computation in the bulk theory itself, right? You have the same
Bulk theory with 1 point.
You
Move
have just added an operator, line operator in the bulk theory.
right. Yeah.
Line
Yes.
integral of the bulk operator.
Yes. Yes. Yeah. Yeah. We actually use the nomenclature that was already there in the literature. Maybe that's a bit confusing. Okay. So these are the diagrams. So this is the 1-point function of so this is the first order term. So here we just have the bulk to bulk propagator with 1 point on the defect, and at the next, this is the next order term. So this is order G. So this is just one diagram, but we will since we have two couplings, we'll have two diagrams for G1 and G2. It will look the same. So here we have one interaction in the bulk. So this red square is the bulk interaction, and the circle black dots are the boundary interaction. So these lines can end in 3 defect insertions in the boundary. And similarly, these are the higher 2 vertices bulk terms. And we can see that up to quadratic order in bulk coupling, we can have 5 defect insertions. So this is order h to the 5 term. So these are the only diagrams that can have, that we can have at this order.
So keep all diagrams in G square.
Exactly. We keep all diagrams in G square, but any order in H.
Yeah. But it really comes to only takes to the 5.
Yes. Yeah. So we can add these diagrams and we can actually compute the defect fixed point, which we can compute the beta function, which looks like this. So here we have h to the 5 term, which is like in here, and this defect, this beta function has a non-trivial fixed point, which is at this value of h squared. So this is the fixed point of the, this is the defect fixed point. So this is the order 0 term, and I have not written down explicitly the order epsilon term.
Just to understand, we have put in the values of G1, G2
Right.
and the cubic fixed point,
Right.
and then set beta of h2 equals 0 to find
Right.
h
Yes.
star.
Right. Yeah. So we are assuming that G1 and G2 we know from the bulk, that is not altered by the presence of this defect. Okay, so now with this defect fixed point, we are now in a position to compute the correlation functions of or the anomalous dimension of any operator, where the theory is at the cubic fixed point together with the defect fixed point. So
Here, like for large n it is like 9. F of n also does goes to constant at large n.
no, it will have some independence here.
Some constant.
I think so. I don't remember the exact term. Yes, yes, yeah.
Usually h2 is small for perturbation.
H is, there is no perturbation.
There is no perturbation in H.
It's exact.
H is exact. So that
Fixed G, that is fixed.
so we have fixed the order of the bulk coupling. So this is quadratic in G squared. So the question is, what are the diagrams that we can have with G square bulk interaction?
And we're keeping all orders in H.
All orders in H. You can see that this term is order H cube. This is order H cube. This is order H5.
So, but still you are expanding the exponential in the Parijat data. Usually minus h.
So there are
No.
When you expand the very finite number of terms,
So, but still,
that does not. The perturbation theory
so we have
truncates.
found a saddle of the Parijat.
But that is in G1 and G2, not in H. Will
The statement is that if you truncate this finite order in G, it truncates the finite order in H automatically without you being
So that's assuming a perturbative expansion.
in G.
in G, not in H.
This doesn't generate some integral of pi square on the line or something.
Integral.
Normally, if you spot up by something, you may generate other operators.
Okay.
But here
No,
that doesn't happen.
no. But is it always the case? Because in other defect kind of theories also, these kind of things are not generated.
I'm saying in the bulk, for example, if you try to write down the beta function,
Yes.
you in general have to include all the operators
Yes,
and their beta functions will get contribution from each other couplings, right?
yes.
So naively, I would have thought the similar things would happen.
I guess this is probably relevant and it's not generating these. If it is some irrelevant information, then probably generate.
How do you see that in the theoretically complete concept?
But we have added this, so this operator we have added from the beginning, saying that we are adding just only one perturbation.
Another statement.
They're relevant.
If you do it for a general operator, in general, to do loops and do things, you have to add more and more.
Okay, that is from the beginning we are saying that we will not look into those
No, but you
operators.
have the choice.
Yes, yes,
You
yes.
say that you add some operators.
Yes, that will, yeah, that will, one will induce that, yes, that's true, yes.
Or some number of terms. And
Right, right, yes.
But then I'm asking, if you're doing a one-to-one function computation, do you even see that those steps will be necessary, if at all they are necessary?
You might. You might not.
Okay.
Here we didn't see any of this. I don't know whether there is a deep reason for that.
No, it should be because it's a relevant information.
Yeah, that's the thing.
Informations.
Yes, that,
Use that.
yeah,
Unless there are other elements.
Yeah.
yes, yeah, there, yeah, I think that this is the only one, yeah. If we can fix the geometry of the defect and the theory, then this is the only one, I think.
For example, does it generate phi 2 because of this?
No, yeah.
The symmetry, because the phi, each phi can be written, yeah, going to minus itself, like phi goes to minus phi, the symmetry is usually for.
I mean, the one can be any of the ends.
Yes, that can be any of the ends. But once you choose one, yeah.
Once you have chosen one, you don't generate the others because of the symmetry.
Have two of those. I am.
Yes. I think then those two will mix, but it will not be phi 3 or phi 4.
Because the thing that rotates the other guys is still a symmetry, as an unbroken symmetry.
Yeah.
Which protects you from generating such things.
And symmetry is broke by adding the
Permutations, but not the ones.
permutation.
Like, see, for example, you can still permute phi 2, phi 3, phi 4, let's say n is 4. Then that is still a symmetry of this Lagrangian, including the deformation. So unless your relevant deformation triggers a spontaneous symmetry breaking, you wouldn't probably generate those guys. But is this known that this is the only relevant symmetry?
I don't think there is a concrete statement about that this is only.
You could have switched on H1 phi 1 plus H2 phi 2.
Yes, yes. These kind of things actually been studied in this paper where they have all the phi i's switched on, and they have shown that it's like the same.
It is also considered like surface defect.
Yes, yes, yeah.
Like dt dx,
Yeah.
tau dx, phi 1, phi 2.
Yeah, so these kind of things have also been studied by Giombi and others recently, yeah. So you can change the geometry of the defect and keep adding terms. So once you change the shape or shape of the defect, you have more freedom you can add more terms, more operators to that. So we did just the simplest case. Okay, so with this, we end up getting the anomalous dimension of the defect operator phi 1, which is computed by using the derivatives of this beta function. And so we take so this involves the derivative of the beta function, and we also have the renormalisation constants. Beta function is set to 0, but we are at the fixed point. So
First derivative of the beta function.
yeah. So this we'll take the derivative of this with respect to h, and then we put this h star. Yes. Delta.
Del H and at H star gives you delta H.
Yes.
I think beta is like the v prime. You are supposed to calculate v double prime and x, right? You think of this as potential.
But then you're making, is this a statement that in the current frequency, that in any arbitrary current frequency, delta is always will be the way
I think that's a fixed point statement.
Yeah, it is. Is that true for any arbitrary currency?
You just needed Z5, right?
Yes, yeah, we have computed, we have computed the renormalization constants. We needed all those.
Just capital and Z.
Yes, yes.
Yeah, see, if you have a fixed point, you go a little bit, you calculate the beta function. That is controlled by the anomalous dimension, right?
It's a function of anomalous dimension.
Yes.
So at beta equals 0, you can find the relation between beta prime and Z, this delta.
Imagine that you have a diamond operator of certain dimension, right? You know, switch on a little bit. You have to find the dimension, switch on a little bit. The beta function associated with the operator is controlled by the dimension, right? The leading term. So that's how you calculate the dimension.
Okay, so should I proceed?
This also finite as n equals to.
Yes. Okay, so
Are these fixed? Do these fixed point become something nicer at larger?
so we have not, so this is still something ongoing, the Largen analysis, but from this we cannot conclude anything which is nicer. Yeah.
Delta looks quite complicated.
Yes. Yeah. Yeah.
Epsilon is positive, right?
Yeah, it's positive. Yeah.
So you can see like then on point to the new the IR point, right?
We are at the fixed point.
Yeah, but still you have 1 point, right?
Yes, yes, yes.
Still it's relevant there, right?
Yeah, it's relevant. Yeah. Okay, maybe I can check the Largen thing. Yeah, we haven't yet studied that seriously. So yeah. Okay, so these are the computations of the correlation function, and I think I would quickly, I am almost running out of time. So these are just the 2-point functions of the correlators, and we can have different correlators of different operators, phi 1 or the other phi's, which runs from 2 to n's. And this is the 2-point function diagram. So this is just the leading order term, and this is the first order in bulk coupling. And we can see that this diagram end up giving something like this. And this is this power law behavior is not surprising. So this is like the behavior of a correlator in a CFT, because along the line we have this CFT structure. And similarly, this is the 3-point function, which again can be computed, and it has a similar behavior. And from this diagram, one can actually compute the OP coefficient or these lambdas. So now let's talk about the 4-point function, the correlation functions. And I will skip, so this is just the Feynman diagram computation. One can do this and evaluate those diagrams, but I will now quickly go through the bootstrap perspective of doing this analysis. So yeah, just okay. So now we would like to study the same defect system, but without any Lagrangian. So this is the framework of conformal bootstrap, where we focus on a CFT itself and not on a specific microscopic realization. So this is the philosophy of bootstrap. So we do not have any Lagrangian, no Feynman diagrams, but we exploit only the consequences of conformal symmetry. So the idea is to reformulate the same physics at the defect fixed point using the language of conformal bootstrap. So what do I mean by that? So since we are on the line, we have one-dimensional conformal symmetry, and the conformal symmetry generators we have, we have one momentum, one dilatation, and one special conformal transformation. And this is a one-dimensional conformal group, so there is no spin, no rotation. And in this CFT, the operators are leveled by two numbers. So this is similar to the usual CFT. So operators are leveled by the scaling dimension delta, which is the eigenvalue of this operator dilatation. And this is the only level the operator can have. So this is something different from the usual CFT, where we have spin and scaling dimensions both. So now we don't have the spin. We also have the operator product expansion, which tells us that the product of two local operators can be written as a sum over infinite number of operators. So we have two operators inserted at point x1 and x2, and this product can be written as a sum over all the operators with scaling dimensions delta. And this is a convergent expression, and the power of conformal symmetry lies in the fact that this the pre-factor is fixed up to this number lambda. So this number is known as the OPE coefficient or the 3-point function coefficient. So these numbers delta and lambda, these are known as the CFT data. So if we can compute all the values of deltas and lambdas that can appear in a theory, we can completely fix the theory. So our goal is to solve for these numbers using the symmetries of the one-dimensional conformal group. Now this is a slide that talks about the irreps of the cubic anisotropic system. I can just skip the slide because we can just, this is just something that applies to ON for n equals 1. So okay, let's just talk about the CFT. So the conformal symmetry fixes the 2-point and 3-point correlation function, and the dynamical information is encoded in the 4-point correlation function. So if we have 4 operators at 4 points, tau 1, tau 2, tau 3 and tau 4, then out of these 4 points one can construct a conformally invariant ratio, which is the cross ratio, which is defined this way, and this 4-point function is a function of this cross ratio only. We have pulled out this factor for convenience, and this delta phi is the scaling dimension of this phi operator. Yes.
So you are trying to study the CFT on this line effect.
Yes, one-dimensional conformal
How will you
symmetry.
ever recover the information that it was a line effect in 3+1 dimensions, or which 3+1 dimension?
That term is not there. So now we are studying the just a one-dimensional.
We will always have to fix. I want to say that this line effect, the fact that it was in some d+1 dimensions,
Yes.
was important in computing the 1-point function and fixing its target.
Yes, but that's the idea of bootstrap. We do not care about.
So those coefficients and all will remain arbitrary.
Those coefficients will be fixed from symmetry. We'll see that even if this is a one-dimensional defect, but what we are studying in, so from the Lagrangian point of view, we are actually at a very particular fixed point. So we are at the bulk fixed point, and on top of that we have the defect fixed point. So from the CFT side also, if there is a solution that exists, that should include that.
Yeah, but some of the data you've already collected, other dimensions, you are not getting.
Bootstrap will always, like fix some range. Range. It won't be in particular.
So whatever explicit solutions you have found will fall in that range.
Sure, right.
So, other epsilon or
Ultimately, that information you are not putting in.
No.
The fact that it's coming from
No,
some bulk
not, yeah, no. We will try to see that some information we need, Bootstrap cannot fix everything. So in that, this information will go, that we have some, but that is not required. Like what I'm saying now, it applies to a one-dimensional CFT. So it is agnostic to the fact that whether the bulk is D dimension or whatever dimension.
Even the ON symmetry.
ON symmetry, so we are talking, so in the bulk, on the line defect, we can have different operators. We can have phi1, we can bootstrap phi1, or we can bootstrap the other phis. So these operators have different scaling dimensions. So we end up getting the whole set of solution. If we solve this equation properly, we end up getting both as consistent solutions. It depends on the correlator that we are looking at.
Maybe the question is how you set up the bootstrap.
Yeah, so the thing is that here we are talking about.
In the previous example that you showed with beta, you got non-trivial solutions, right?
Yes.
Here the h equal to 0 you have also made a solution.
Yes, the defect, the trivial defect.
Yeah.
Yeah, h equals to 0, I think, yes.
That will also solve the beta.
Yes.
That will also come out of the bootstrap.
Yes, if we solve it properly, it will, because that will be the free parts of free solution, yes. Yeah.
But it's not free in the sense that the 2 and 3 point functions are all still non-zero, right?
Yes.
In the, even for h equal to 0.
Yes, so one thing is that, like, when we talk about, it depends on which correlator we are bootstrapping. So when we have these kind of correlators, we have phi1, which we use to break the symmetry, and we also have the phi a hat, so a hat runs from 2, 3 to n. So these two operators will have different scaling dimension, and it depends, so
But
both these
at the trivial fixed point, they have the same scaling.
They have the same scaling dimension, exactly. So at that order, it will not be possible to distinguish them. I will comment on that. Yeah, that's true. Okay, so we can expand the correlation function in the S channel conformal block, where we have operator 1 and 2 close to each other. So this is the S channel expansion, and this G delta, this is the conformal block, which can be written in terms of this hypergeometric function. This is a Gaussian hypergeometric function with some prefactor over here, and this coefficient A delta, this is related to the OP coefficient. So in this expression, the CFT data is lies in these deltas and these A's. Now we could have as well expanded this in the T channel, where we have operators 1 and 4 close to each other, and this is equivalent to changing Z to 1 minus Z. Now if operator product expansion is associative, then these two expansions should give the same result. So this is the equality of S channel and T channel, and this is the bootstrap equation in one dimension. So this is a functional constraint on the CFT data. So this puts a constraint on A's and deltas, and this has to be satisfied for all values of Z. So the goal of the bootstrap program is to try to find a solution of this equation. So if there is a suitable solution exists, so then that will tell us that this is a specific CFT. Okay, so this equation can also be written like this, and I'm going to skip the technical details. I'm just I will. So there are different. So this bootstrap equation is in general complicated to solve directly and to extract the coefficient. So we need different techniques to solve this equation. So here we have used the analytic functional tools to solve this bootstrap equation. So this was developed by Mazak and Paulos in 2019. So the idea is that we have the bootstrap equation, which is a functional equation, and we act on this equation with some linear functional. So this linear functional acts on this bootstrap equation and give us some algebraic equation. So the basic idea is to map the functional equation to an algebraic equation. So this linear functional can be, we can think of this living in the dual space. So with these analytic functionals, we can we end up getting these kind of algebraic constraints. So these are two constraints with alpha and beta being some functions which I have not written the explicit forms, and here we do the z dependence is gone. So this is a purely algebraic equation. So we can actually try to see if we can solve this equation and get the values of deltas and a's. So these sum rules, these are known as the sum rules to constrain the CFT data. Now this idea of this analytic functional things, this is similar in spirit with the Polyakov bootstrap. One can show that they are equivalent. So this was developed by Gopakumar Kaviraj and Ansina in 2017 and subsequently studied also in these papers. So one can try to solve this equation, and we have solved this equation, and what we need to do in order to solve this, we need to assume something about the spectrum. So this is some kind of assumption that we make. So we assume that in the operator product expansion of two field phi i's, we have the identity which is always present in the spectrum, and we have these kind of operators consist of two phi's with 2n number of derivatives acting on these phi's. So these kind of operators, they are known as the double trace operators, and these operators can have same Baire dimensions. So all these operators, at leading order, the dimension is 2 plus 2n. So I think this is what you were talking about it.
So here you're not actually contracting the twin operators, like Li and if you contract the del squares can be removed.
You mean this I and
Box n is just n derivatives.
n derivatives, yes.
Which are not contracted.
Yes. Del mu, but it depends on which operator product expansion you are looking at. Yeah, in general, one can have all the operators.
These are derivatives along the line or transverse to a line?
Okay, that is our tau thing. So from the point of view of bootstrap, so we are now along the line. We do not know whether there is anything else in the universe.
Delta to
Sorry?
delta to 2n.
Yes.
The box is just derivative.
Yes. Yeah.
Yeah, delta square.
Yes, just because here we do not know that whether there is any higher dimensional theory or not. Yeah. So these are the operators. So what I'm trying to say is that all these operators will have the same Baire dimension. So it will they will mix. So these are kind of degenerate at this order. So it is difficult to tell us which operator is this particular one from the bootstrap point of view. So, and this is the operator, the P coefficient. So the idea is now to use the analytic functional equations and try to and we assume that the CFT data can admit an expansion in this epsilon thing with all these gamma i's and a's being something that we would like to determine, and try to solve this equation order by order in epsilon. So we can do that. I have just written this simplest term. So this is just for the ON model, and this is less clumsy. So what we have, so we have some average expression which involves the order 1 anomalous dimension with the 0th order of P coefficient. So this is something that this combination is something that we get. We cannot talk about the individual gammas. Averaged over all the, okay, so averaged over all values of n.
Averaged over n, then you can't have n
Okay, so yeah. So we have all these operators, and we have, for different operators, we have the same scaling dimension at 0th order, and
Same thing.
so sorry, yeah, different eyes, yes, sorry, yeah. So these n is fixed, yes. So these are all the operators that we can have, and we do not know which one of the anomalous dimension we are getting. Does that answer?
So there are n degenerate or n minus 1 degenerate.
Right. Which cannot be fixed, at least at this order, which cannot be fixed from bootstrap. So that's
Any degenerate operators, because we can't distinguish between the defect operator and the others in the main field.
Phi 1 and phi 2 may have different dimensions.
but that is
Because
at
one
the,
is concerned, right, with the support of phi 2 outside the line.
that is not included here, right?
So phi 2 and phi 1 seem to have the same Bayer net.
Yes, that's over here. We just put n equals to 0.
Right. So phi 2 will be the second component of the vector.
So these operators. So yeah, these things are not included in this expression. So this is only of this. So this is the only of this, and the scaling dimension of these operators, these are taken as an input.
And you fix the Bayer dimension to be the
So
same.
here,
Bayer dimension?
To be the same for all.
Yeah, so this is the Bayer dimension, which is same for all of these kind of operators.
Including phi 1. Even though phi 1.
Yes,
your
yes,
previous
yes.
Lagrangian way of looking at it, phi 1
Yes.
was different, right? Because
Yes,
of the defect.
that's true. Because here it doesn't know what is the bulk theory. So it's not possible to say anything about that. Yeah, sorry, Luga, you have a question?
so here you're not summing over, so when you're,
So-
you're thinking of fixed I, no sum over I as one operator. And you're averaging over I.
Yes. So for each I we will have some operator, but we cannot say which operator is it because they are degenerate.
Yeah, okay.
So that's this average thing. And here we see that this average is fixed up to this undetermined constant. So bootstrap cannot fix this. So this is the value of the first operator in the OP. It's like the phi squared. So
So
the
the phi 1 OP,
right.
looking at phi 1 delta to the power 2 in phi 1, and that,
Yes.
that term has the data.
Right.
You're saying if you know that data, you can determine all other OP.
Right. But what I'm trying to say that this part cannot be fixed from bootstrap. So with this method, so we need some, because there can be other theories with the same anomalous dimension. So it doesn't know about this.
How does the gammas go with the little n?
With little n, we do not actually have the explicit expression for gamma. We cannot disentangle this. So we can only,
You have some, I don't know, like, okay, so
from this expression, we cannot comment about the individual gammas because
like if the dominant contribution comes from, for example, where you have large n, then it might be
large n, you mean capital N? Little n.
yeah, that's because you have all the derivatives in all, right? Like box n.
You mean the higher orders in n?
Like in the OPE, you have
Yes.
all these different contributions with different parts of little n, right?
Different powers of little n, yes. But we do not know which one is the dominant contribution, right?
Like this, is there another of the large spin bootstrap?
Yeah, something like
Large spin bootstrap.
just you have a line, right? Yeah.
Yeah, so effectively like this large small n.
Yes.
All these things are large small n.
Yeah, we have not, it could be possible that we can gain some mileage out of this, but this is, yes.
Yeah, here there is only one dimension, right?
So the question is if we can have some analog of this n, which is in the large n limit, simplifies the equation so that we,
I guess
It's
you
not
can.
about simplification. All I'm saying is like I don't know if there is some argument where the dominant contribution, for example, comes from where it is very large, then yeah, of course it will simplify, but I'm just also just one question. So the scaling dimension for phi2 will be also the same, right? That the defect.
The leading order term.
Why? Because because the IR, the scaling dimension of phi1 does not get any contributions from other.
Does not get what? Sorry.
The contribution from other effects. I don't know. Maybe this is okay. Do you have like an expression for phi2 like the dimensions?
No, we cannot actually compute. We cannot present
not
an.
from this, but like from the earlier, like using like the Lagrange.
Yeah, it is there in for some specific operator. It is there in the paper, but I have not written it in the slide here.
You're saying it changes, right?
It changes, yes. Phi 1 and all the other phi's will have different scaling dimensions. Okay, so yeah, so the bottom line of this slide is that if we use the bootstrap analysis, we can fix the corrections to the OP coefficient and the average values of the anomalous dimensions up to some unfixed parameters, which depends on this. Now,
What's the superscript?
this is some number which.
Superscript on A and R. Subscript is that N.
Okay, so this is the order 0 correction. So
In epsilon.
yes.
Power of epsilon.
Or so yeah, so this is yeah, so this is the order 0 term, this is the order 1 term, yeah. Okay, so now that's what we can fix from bootstrap, but at this level if we want to fix this, we have to use this input from some other theory. So here comes the role of the Lagrangian. So if we want to really connect it to the theory that we are considering, then we have to compute this from the Feynman diagrams or the specific theory, and then we can use the fact to determine these kind of spectrum. So, and if we use these results from the Feynman diagrams, then we can actually cross check that at order epsilon we resum these all contributions and we end up getting the 4-point correlation function from the Feynman diagram. So this is kind of a consistency check, but this thing we need to fix from the Feynman diagrams. Okay, so that's all, and yeah, I'll skip this order epsilon square. This is just so. Now let me summarize that we have studied this cubic anisotropic model with relevant deformation, and we have used two methods to study this. So the first one is a Lagrangian based approach where we study the renormalization group flow, and we have shown that there exists a non-trivial fixed point when the bulk is at the cubic symmetric fixed point, but throughout this we have assumed that the defect is general. So we keep all the terms, all the defect insertions terms at any order at any given order in the bulk coupling. And towards the later part of our talk, we used conformal bootstrap framework to study the correlation functions, and we have shown that it can fix the correlation functions by assuming some input from the Feynman diagrams, and also for both for the OP coefficient and the scaling dimensions. So it's kind of a complicated thing to just fix from the bootstrap, so that cannot be done as it stands now. So now, so this is the last slide. So there were already some questions about this large N defect line. So this we are currently exploring, but as of now we do not have anything nice to say, whether it simplifies or whether it does not. So we have to see. And one can actually try to see what happens if we go away from the criticality. So we just we are not at the fixed point. We just have general quantum field theory. Then we add defect.
Cubic fixed point itself, one understands the large and limit. The bulk fixed point.
Yes.
That has been studied.
There, yeah, so in this sense that there is some critical value of n that was established using different approach, and
I'm not talking about the value, but I was saying, let's say I take n to infinity. Can I determine G1 star and G2 star for orders?
from just from n equals from the limit n equals infinity.
Can I determine it exactly? Can I resum the diagrams?
Okay, that is a good question. I do not know the answer. Yeah. So we did some large analysis of this cubic symmetry, but that was purely a bootstrap approach. So for this G1 and G2, I cannot comment on that. Yeah, it would be nice to see if there is something concrete that can be said from this. Yeah.
But, this aspect is true that at large enough, I mean, these three fixed points are there, Heisenberg and cubic.
These things, yeah, this is a generic n statement, I think. This should not be altered. Now the question is whether it simplifies to something nice at large n, that needs to be seen.
These kind of things, vector things, at large and they just become free.
Yeah, I'm not sure if.
It seemed like a Gaussian fixed point, the answers you had.
Yeah. So from directly from the fixed point structure, I cannot comment on whether it will be.
No, I'm asking this question, that if you put G1 star and G2 star as a function of n
Yes.
and take n to infinity,
Yes.
thus G1 star and G2 star becomes 0.
No, I don't think so.
Becomes a finite.
Yes. Yes. Yeah. 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 Yeah.
Just G2 star goes to 0, then it's question.
Like you want G1 star also to go to 0.
So G20 is Heisenberg.
Yeah.
Oh, sorry.
But yeah, I don't think it goes to 0. But yeah, again, I am not sure. I have not checked it explicitly.
That's interesting because usually vector largesse are usually
Mm-hmm.
here it is not.
But in any dimension, you expect this to be true.
No, I'm talking about the Wilson-Fisher.
Wilson-Fisher. Okay. So first epsilon and then large n. Yeah.
Usually, like, so if you say Wilson-Fisher, definitely large n is.
Yeah. Yeah.
So if you have G2 equal to 0,
In the Wilson-Fisher.
you will get Wilson, that's just Wilson-Fisher.
Yes.
So then, there I think G1 star just goes to 0. If you take anything. Here you're saying that doesn't happen. I do not know what happens if you.
Yeah, I'm not sure. I'm just guessing that this will, both of G1 and G2 may not go to 0. Yeah.
It goes on and
Some other theory would be, I don't know. Okay.
Some other theory which in the large n limit goes to 0.
Going back to an old question.
Yes.
In the physical system that you make lattice, like you were describing this.
Yes. Yes.
In that, what is characterizing these spirals?
It's light of the spin. You can think of that at each lattice side. I mean, usually, so let's talk about the Ising thing. So, Ising model, so two-dimensional Ising model, 2D or 3D, whatever, or just ON model. So then we, yes, so here also this is some kind of this. So the character, instead of spin, we have these atoms at each lattice side.
It's an ON valued object.
Yes.
Trying to figure out what is that ON valued object in the lattice.
You mean with the n component, what is the object?
Some ON valued object you want on the lattice in the system.
Yes.
Something that varies.
But this n stands for the rotational degrees of freedom.
Yeah, so
So,
internal symmetry,
yes,
some internal,
yes.
what is that?
This is the structure. Yeah, so this is the structure that was there. From one structure it goes to another with some crystal symmetry that breaks the rotational invariance. So if your question is what exactly does the phi measure, is it the question?
See, for instance, spin can measure the magnetic in the right hand side, right? Ferromagnetic or
Yes.
whatever phase it is. I'm trying to think of it in that way.
I think the idea is similar, but I cannot make a precise connection with this with the context of this atom, which property of the atom.
Yeah, because I'm not able to imagine these degrees of freedom linked to these lattice sites.
So G2 equal to 0.
Yes.
Generally, what you do is like you just type the tetragonal lattice sites, website tetragonal positions as cubic positions plus a perturbation. And the perturbations are characterized by some order parameters. Right? That's what you would do.
So if it's actually characterizing the position, then it's linked to the dimension of the space.
No, but you see, the positions are all not independent because it's not like like the full cubic symmetry is gone. You want to break it into tetragonal. So there's a small number of deformation
That allow for this.
that deforms the cubical tetragonal.
But your question is precisely what is the quantity? So,
So I would think it is just like extending this cube. But,
yeah, so that.
how is that ended? But that sounds like like it would be a quadrupole definition.
So this is just for n equals 3. You can think that it has 3 axes with phi 1, phi 2 and phi 3.
You're saying it's a vector.
Vector, yes. I'm answering his question.
It's not some.
So you can cubic lattice only if you turn on both G1 and G2. If you turn off G2, you're left with the fully rotationally very medium, like the orientation of the octahedral.
No, that's a continuity.
No, I think you introduce G2 to bring in just the discrete cubics.
Yeah, that's all. That's right. But what I'm saying is, what is the phi?
What is the phi?
Yeah, and to understand what phi is, if you turn off G2 then it will be the orientation of the octahedral in three-dimensional space. That's the
Yes.
G2.
So I think it's the rotation, so the rotation angle and the rotation length. This. No, I think just the pure rotation angle and length, that is.
You can just add a z square. If you add a quadrupole deformation, it will get expanded in z. So then it will be rotationally symmetric with x, y. But it will also, but this deformation sounds z going to minus z. So I would think it's a quadrupole deformation. So then I would think it's like n would be 5 or something. But you're saying it's
No, it's n is 3, no?
So that tetragonal thing is spontaneous symmetry.
yes. So that's the order parameter. So then that is 0. That the quadrupole deformation is 0. It is cubic. Then it is turned on. When it gets a web, it becomes tetragonal. So I think it's a quadrupole order parameter, but you're saying it's a dipole order parameter.
I would think that it's a 3 component thing. Yeah.
So this is what I don't understand because tetragonal doesn't break the z going to minus z.
No.
So, but the dipole order parameter will break. Dipole is like a vector. It's along one direction, and it doesn't. It's not reflection invariant.
Right.
Because of parity.
Yeah, it doesn't. Yeah, it breaks parity. If you put a wave for a dipole,
Right.
it breaks parity. But the tetragonal breaking seems parity. The reflection symmetry, the vertical reflection symmetry is not.
Also, this kind of thing, this model is also used to describe cubic to trigonal structure, where we deform it along the diagonal of the tetragon or the diagonal of the cube. Yeah.
No matter what, parity is not possible because everything is
Phi symmetric.
phi square position or phi.
Parity is there, but crystalline parity is different from how you
you're
should
talking
relate
about
to
the file which.
how the target space parity in this phi is there. They will
No, but each of them is preserved. That's what I'm saying. No, Lagrangian that was written.
the Lagrangian is a full cubic symmetry. Lagrangian you cannot see the symmetry. The question is the phase when it gets a wave, how much symmetry does it give? And one more question, so just this going back to the bootstrap. So bootstrap got some results. Was that there was some matching between that and the Feynman diagrams?
Yes, yeah.
So and you match A0 come out and check that.
So no, so the matching is, so in, okay, so just this one. So here these are the quantities that we can compute from Feynman diagram. So we can compute
So you
both.
check these two relations in Feynman diagram?
Yes, in this sense that what we did is we first use this expression from the diagrams, we plug this in here, so we have this expression, and in principle then we can resum this thing to compute this correlator, because we now know everything, and this correlator is matched to the Feynman point function computation. Yes, yeah. Thank you.